We're here to have Jorick Vink from the Armagh Observatory. So he will talk today about the mass laws in massive stars. And let me say some few words about his CV. So he did his undergraduate studies on Utrecht, and then where he also did the PhD under the supervision by Lammers on mass laws in massive stars also. And then he had a postdoc at the Imperial College during 5 years in England. And then he was for a year faculty, had the faculty position in Kyle. And then he is currently at the Armagh Observatory, where he is also a faculty member. So thank you very much for coming. So as you know, this is within our series of inviting people that is going to the Roque de los Muchachos Observatory, and we kindly asked them to give us a talk, and he has agreed. So we thank you very much for coming and giving us the talk. So go ahead.
Save that. Is it okay? Yeah, okay, now it says okay. But it might be that I'm just shouting hard enough. And therefore it's okay. Anyway, it's very nice to be here. It's also very nice to have temperatures over 20 degrees, something we don't even have in July, so you must be very lucky to have it in November. But yeah, so I'm going to La Palma, actually looking at both O stars and Herbig stars. So actually this picture captures two of my interests in astronomy, both massive stars and star formation. And you see they're actually related, because here you see a cluster of massive stars, and you see that the effect of the massive stars in terms of energy, momentum, and also ionizing radiation, you can see its effect on surrounding regions. You see the ionizing radiation triggering new star formation here. So the two topics are very much related. And the other point in this talk, actually, that I say here, the fate of massive stars. If you look at this object here, this is a B supergiant, highly evolved. Theory says it should not explode. But if you look at the mass laws, the circumstantial environment around this object, it looks actually very similar to the ring nebula around 87A. That was a supernova, so who knows what happens to this one. Maybe it will go off very soon. So this picture actually captures a lot of the formation, the evolved massive stars, and also evolved stars. Okay, what I'm doing, yeah. So I'll give a brief outline of this talk. First, an introduction on mass loss. Why do we want to understand mass loss? Because it's very important for stellar evolution of massive stars. It's really driven by mass loss, the evolution. And I'll basically tell you how we're going to predict mass loss rates. I'll describe two methods. This CAK is a paper of 1975 by Castor, Abbott, and Klein. And in the massive star community, we just refer to this as CAK. And everyone knows what you're talking about. So maybe I shall talk about that a bit later. First is Monte Carlo technique. That's a method to predict mass loss with multiple scattering photons. I'll come to that. And using this technique, I'll present results for O stars. And when we have tested the technique for O stars, we can go to low metallicity systems, like the SMC and the LMC nearby. We can test our predictions against observations in those systems. And then towards the end of the talk, I'll discuss this term bistability jump. Something that you may wonder, what on earth is that? But I'll come to that. Luminous blue variables and the relationship between these two. And luminous blue variables are very unstable stars that are highly evolved, but they're not supposed to explode. They are supposed to have high mass loss and become Wolf-Rayet stars. But at the end of the talk, I will claim that maybe some LBVs are already directly going to explode very soon, and I'll come to that. So why would you want to predict mass loss rates? As you saw on that first slide, there's energy momentum input into the interstellar medium. And if you look in the star-forming region, the first 7 million years, actually it's the winds, mostly of Wolf-Rayet stars, that dominate the energy input. And then later on, the supernova take over. So if you look at a star-forming galaxy far away, and if you're really interested in the early phases, you really need to understand the mass loss. As I said earlier, why does this not work? Okay. Stellar evolution. So for low mass stars, we know that the evolution is mostly driven by what happens in the core of the star, but for massive stars that is very different. The most important aspect, especially for the most massive stars, is what happens outside the star. If you start off with a 60 solar mass star, you end up with only 6 solar masses before you explode. So clearly you need to understand mass loss if you want to understand anything about the evolution of massive stars. So a picture here of Russell diagram. So you see the upper part, you see O stars on the main sequence. You see luminous blue variables. These are very unstable stars that on timescales of years, they are highly variable with highly variable mass loss rates. And we don't observe any red supergiants here. This is the Humphreys-Davidson limit. This is an empirical limit, and it says that red supergiants are not allowed to be here because they're not observed. And we think that this is related to the Eddington limit, the theoretical Eddington limit, that stars just cannot, they become extremely unstable, have high mass loss, and because of the high mass loss, they will end up as Wolf-Rayet stars, where they are much less massive. So if there are 60 solar masses here, there are only 10 solar masses here. And there, because the stars are suddenly much smaller, they still have very high mass loss rates, so they have very dense winds as well, with fast winds, and you get strong emission lines, characteristic of Wolf-Rayet stars. And the idea is, theoretically, this is where the stars are burning hydrogen in the core, the hydrogen main sequence, and the helium main sequence is here in the Wolf-Rayet phase. So 10% of their lifetime should be spent here as a helium core burning object. So if this is a 2 million year period, then this should be a 200,000 year period. And only after that you get core carbon burning, core oxygen burning, etc. And then you should explode. So that's theory. What do the observations of supernova tell us? Well, so far, all we know about collapse supernova is that stars up to 20 solar masses explode as red supergiants in this part here. And they give rise to type 2p supernovae in this part. What happens to stars more massive, 25, 40, 60, 80, etc.? We have no idea. Theory tells us they should explode here, but what is this all excluded? Maybe theoretically, but maybe observationally it's not. So these are the kind of questions we want to address, and for that we need to understand the mass loss. Somehow this doesn't work particularly well. So the mass loss is important for two reasons. One is that forward prediction of stellar evolution. If you want to understand the forward evolution, you need to understand how much mass is being lost. And the other point is that if you look at observations of supernovae or gamma ray burst, you can actually look at the circumstellar medium around it, and maybe by probing the mass loss history back, you can actually observationally learn about, through the mass loss, you can learn about what was the progenitor. And as I said earlier, if you start with 60 solar masses, but you end with about 6, then clearly you come in a range where you don't know anymore whether you're going to form a neutron star or a black hole. So ultimately that will be set by mass loss. And that has consequences for X-ray populations in galaxies. If you look at nearby galaxies, different metallicities and so on, will you have high mass X-ray binaries, will you have ultraluminous X-ray binaries, etc. That will depend on the mass loss. So clearly it's important for evolution. Then it's important for stellar spectra. If you look at an individual star, an O star, you have UV lines. I'll show you a couple of examples. But if you integrate all that light and you look in external galaxies, starburst galaxies, then the integrated light will show nice Cygni lines. But to understand them, you need to understand the stars that produce them for the analysis of starbursts, like starburst 99 type models and so on. And the prediction of ionizing fluxes in nearby starbursts, but also actually at very high redshift, because there's an issue of what reionizes the universe. And one of the potential possibilities is massive stars, the ionizing flux from massive stars. So if you want to know how much ionizing flux is produced, you actually need to know whether these stars have mass loss or not, because a star with mass loss has a completely different spectral energy distribution than a star without mass loss. So then we come to stellar cosmology, basically. Particularly, so if you start with the Big Bang of just hydrogen and helium, and you have an expanding universe, and everything gets less and less dense, at some point you still manage to form stars, and you come out of the dark ages, and suddenly, after about 100 million years, the first stars form. And theory tells us that these stars should be very massive, like 100 solar mass stars. And their mass loss and their evolution and their supernovae will be enriching the interstellar medium, and you get the whole buildup of chemical elements from Z equals 0 to very more to the solar type galaxies that we see here. And the idea here is that these stars, in these computer simulations, people include just gravity basically, and they form 100 solar mass stars. But the radiation pressure is not included normally in these calculations. So we don't know if these stars are really 100 solar masses and they don't have mass loss, or whether alternatively they might look more like this one, a very massive star nearby, the only really 100 solar mass star that you can see, and you can clearly see that this star has lost a lot of mass. So maybe it is not as simple as that. So why is that interesting for cosmology? Well, if you look at yields of the first stars, and this Hager and Woosley plot has been shown a lot, if you have initial mass on this axis and final mass on that axis, if you have no mass loss, you have this one-to-one relation. Now here you have stars up to 10 solar masses or so make white dwarfs, and then neutron stars up to about 30, and then between 30 and 140 you get black holes, and then between 140 and 260 you have something quite special happening, predicted pair-instability supernovae. These will completely disrupt the star. You get no black hole, but all the metals are dispersed into the interstellar medium. And then above 260, you get black hole formation again. That's what theory tells us. But in these calculations, as you can see, there's not a lot of mass loss included. But if you would have a lot of mass loss, if you start with a star of 200 solar masses, but you have a lot of mass loss, you may end up with just a 10 solar mass star. So we don't know. So we don't know whether these pisons exist. And this is the kind of thing we need to find out. And that is all determined by metallicity-dependent mass loss. Now, you need to do this from theory, because observationally, this is all we're going to get. It's not a lot, because this happens so far away. So the only way to do it is from theory. So the goal is to quantify the mass loss as a function of metallicity and redshift. And before you can do that, you need to know, what do we know at solar metallicity, where you can observe the stars individually. Now, we know O stars have Cygni lines. There we go. This is an O star with this telephone number. You see a Cygni line clearly, and the terminal velocity is determined from the blue edge of this profile. And this can be done quite accurately. People think about 10% accuracy that you can achieve. And you will find for normal O stars terminal velocities of 2,000–3,000 kilometers per second. And that is quite an accurate measurement. Yes, there's a lot of variability in these profiles, but this is quite accurate. Now, in reality, these winds will not be stationary, they will not be smooth, they will be clumped, and that will affect the ionization. So it is much harder to determine a mass loss rate from these profiles. You can do it, but there might be a large uncertainty. And this uncertainty could be factors of 3, factors of 10. People have even suggested factors of 100. Now, that would be clearly completely damaging to anything we know about massive stars. If the mass loss rates, because of clumping, are a factor of 100 lower than predicted, that means that mass loss is insignificant for stellar evolution, at least on the main sequence. And then maybe you need only these LBV type eruptions. But I don't think this is the case. I think the mass loss rates are quite high, but I'll come back to that. So the theory was developed in the 1970s, and the principal mechanism is quite simple. You have a star with lots of photons, and these are intercepted by atoms in the wind, and the first absorption is coming from the star, but the re-emission is more or less isotropic. So there's a net outward acceleration, and if that's higher than gravity, then you get a mass loss. And that mass loss rate will depend on the opacity, so depend on the metallicity, but it will also depend on the other stellar parameters. The more photons you have available, the higher the luminosity, the higher the mass loss rate. The lower the mass, the easier it is to escape the potential well, so the higher the mass loss rate. It also depends on the temperature of the star, because the temperature sets the ionization in the wind. So if you have iron 4 lines, you have a certain set of lines driving the wind, but if you recombine, and you get iron 3, it turns out you have suddenly many more lines available, you have a higher force, and you actually expect more mass loss. Actually contradictory to what for some reason some people think that if you go to later type stars that the mass loss rate would somehow drop. Theory actually predicts they will go up, but I'll come back to that. So these are the kind of parameters that are important. And the theory, the underlying theory that was developed in the 70s is this Kastler-Abbott-Klein theory, line-driven wind models. In this paper, they looked at the distribution of lines of carbon-3, and it turned out if you parameterize that in a simplistic way, there's two parameters, you can plug that into the equation of motion, you can consistently solve for the mass loss rate and the terminal velocity of the wind. So you get a velocity law from the photosphere, 0, up to a terminal velocity, and the steepness of this velocity law is given by a beta. A beta is about 1, and it tells you where most of your acceleration occurs and how fast that happens. And it turns out that this terminal velocity that you reach, so for O stars this is about 3,000 kilometers per second, it's actually a constant. It's about 2.6 actually, times the escape velocity of the star. And that's for O stars. But that is not necessarily the case for other stars, because other stars have different lines driving the wind, so you might have different constants. But you would still expect this relationship. And the theory also predicted that the mass loss rate scales with the luminosity. And that has been proven to be correct. The mass loss rate does go up if the luminosity is higher. So the underlying theory works, but it doesn't work in terms of the, if you compare it with observations on the kind of accuracy that we want for stellar evolution, because you want the mass loss rates to be accurate within a factor of 2. Because if the mass loss rates are off by a factor of 2, you're already completely in a bad situation. So the fact that the mass loss rate that CAK predicted, based on this carbon-3 atom, is actually completely fortuitous, because we now know that carbon-3 is not a very important ion in massive stars. It's actually iron lines that drive the wind. So it was basically good luck that the mass loss rates were quantitatively correct. I mean, qualitatively, it's a very nice theory, of course. So there's a couple of interesting problems for which you need more sophisticated models. And one is that there's a momentum problem in stellar winds, or there was actually up to a few years ago. I will show you what that is. We want to understand this metallicity dependence of mass loss, and we want to understand this bistability jump. So the momentum problem, if you have the most sophisticated CAK-based models, these are the Munich models, if you divide those rates by the observed rates, and you plot them against observed mass loss rates, if they are in perfect agreement, they should follow along this line. They should scatter around this line. But they don't. There's a growing discrepancy, and it is systematic, and it grows with increasing wind density. For the most massive O stars, this is already off by factor 10. This is a log plot, so this is 1 dec, so there's a factor 10 off. Now, how can you solve that momentum problem? Suddenly, you somehow need to transfer more momentum from the radiation field to the outflowing particles, and one way to do that is with multiple scattering, and that was why Abbott and Lucy had this very nice paper where they showed that with multiple scatterings you can easily go over the single scattering limit, and by factors of up to 10. And the way it works is the photons, you follow photons from the stellar core into the wind, and at every point in the wind they're allowed to scatter many, many times, and you have a cumulative effect where you dump more and more momentum into the wind, and you get much more momentum than in the case of a single scattering. And this is the kind of approach we are also using to calculate mass loss rates. So in our approach, which is an updated version of this previous picture, because it includes continuum processes, which were not included by Abbott and Lucy. But we assume this beta law. So this is what makes our approach semi-empirical. We use knowledge from Cygni profiles, the terminal velocity of stellar winds, because that's accurately known within 10%, and that goes into the model as a first step. Then we compute model atmospheres, and we calculate the ionization certification of the important elements, hydrogen, helium, CNO, silicon, etc. And compute level populations, and then with the Monte Carlo approach, but similar to one I showed earlier, we calculate the radiative acceleration at every point in the wind. And this is what we did a few years ago. We did a large parameter study of massive stars all over the upper part of the Hertzsprung-Russell diagram, with many models at each of these points. And we calculate the rates, and the rates are given here. This is a complicated plot. I'm sorry to show it, but I just want to show you that we have rates for different luminosities, masses, temperatures, metallicities, etc. And that led to a recipe that is now mostly used in most stellar evolution models. And if you plug in the stellar parameters into the recipe and you compare them with empirical rates, so this is a similar plot as I showed earlier, then, so if the two are in perfect agreement, they should be along this line, and as you see, there's no longer any systematic discrepancy. There's a huge discrepancy though, scatter. And this is largely due to the fact that these are galactic measurements where we don't know the distances very accurately, so we don't know the luminosities very accurately. So it's not very, so for an individual object you might be off by quite a bit, but there's no systematic discrepancy. So to summarize the two approaches, basically you had the CAK type approach, where the line force is approximated. That's a drawback of this approach, but then you actually get the dynamics right, and you get this beta law. And this other approach, where you adopt this beta law, and then you calculate the line force at every point, including multiple scatterings, and you get a more accurate description of your line acceleration. Now, in principle, there's nothing stopping us combining the two approaches. When we adopt a velocity law, we basically, we also assume a corresponding line acceleration. If you say this velocity is caused by a line acceleration. And at the end of our calculation, we have a line acceleration. So we can actually iterate the two. I mean, as a function of radius, you can just say, oh, where are we? How dynamically inconsistent are we? And we just shift the beta at that point. So we can iterate, and we can do this better. And we have recently done that, and I'll show you the results of that. Yeah. And that's given here. So what we have done is we have described the line acceleration as a function of just radius, and we have fitted it. And here is the final result. This is at the end of the iteration process, where the Monte Carlo line force, the dots, are given with the dots, and you see our fit with the dash line. So this is at the end. It was at the beginning, you would have a big discrepancy between the two. And in this iteration process, you start with a low mass loss rate of 10 to the minus 7, and a high terminal velocity in this case of 7,000 kilometers per second or so. And then after about 10, 15 steps or so, you see that you converge to a high mass loss rate, 10 to the minus 6, and at the same time we also reach a terminal velocity of 3,000 kilometers per second. And that is observed. So we now, although the recipe that I provided years ago is mostly based on semi-empirical results, in principle, this is no longer necessary. We can do all this now self-consistently. I don't know if it's going to make a big difference, because the mass loss rate we find is exactly what I found earlier using this semi-empirical approach. So the semi-empirical approach was actually very good, and we thought it was good because the terminal velocity is so accurately measured. But if you want to go to the early universe, of course, you can't observe terminal velocity, so you have to do it from first principles. And now we are in a situation where we have no longer any free parameters. So, of course, we still use atomic data, and if that's wrong, then our predictions will be wrong. And we make assumptions. We assume the wind is smooth, and we assume it's time independent, and so on. So there are still many issues to worry about, but there's no free parameter, there's no fudging. It's a real forward prediction. Nothing is inferred a posteriori. But I think on the basic results in terms of the wind momentum luminosity relation on this axis versus the luminosities, here were the observed data, and this was my theory. I don't think this is going to change much, but maybe we'll find some surprises here. But I think the situation is good enough to go to low metallicity. So that will be the second issue I want to discuss. So if you go to low metallicity, here you find some predictions as a function of the mass loss rate versus the metallicities. This is the solar case. And as you see, there is a steep dependence. And we have calculated models only up to about 100 of solar. So this is the observable universe, I mean, where we can still see stars. The question is, what happens for stars at even lower metallicities? Will this continue to fall? Will it fall that way? Will it fall that way? These are all kinds of questions that are still open. But the point is that in the local universe, there is a steep dependence, and it's about 0.7, and that's a bit steeper than mostly quoted square root dependence. We can test this, and this has been now possible with a large program on the VLT on massive stars that also Herrero and his group are involved in. That's the FLAMES project, over 100 hours of VLT time, and looking at 700 stars. Most of them will be stars, but in the future we'll do 1,000 stars which have many, many O stars. But in this project there were 100 O stars scattered between the galaxy, the LMC, and the SMC. And here you see the data. When I say data, I actually don't mean real data, because you need to do a lot of analysis before you reach those values. And so you take a spectrum and you model it with fast wind in this case. It's a complicated process, but at the end you get mass loss rates, temperatures, gravities, terminal velocities, etc. And if you look at the values, they are, so the solid lines are these observations. You see they are very nicely aligned with each other. And so there's a very clear wind momentum luminosity relation. And also, for the first time, we now see that the LMC data, so this is 40% solar, are in between the galaxy and the SMC. SMC is about 20% solar. And if you derive the mass metallicity dependence empirically, you find a value that is consistent with theory. So that's very good news for me. But if you have good eyes, you can also see that the empirical rates, these solid lines, are above the dashed lines. So the dashed lines are the theoretical rates. And the offsets are quite similar, but they're offset. And mostly in physics, when you see data and you see theory, you say, okay, theory is too low. But that is not what most people think in the field. The people think that it's actually the empirical rates that are too high. Because in this analysis, you assume the winds are homogeneous. Whereas if they're clumped, you overestimate the mass loss rate. So these are really upper values, these rates. Now the real question is, if you lower the observed rates by a factor 2 to 3, they are in perfect agreement with theory. So that would be a very good situation, because then everything that we put into the models, at least in terms of massive star models, would be working perfectly fine as it is. There is, of course, the possibility that both are too high. So that if the mass loss rates are, I don't know, too high by a factor 10, and that somehow the theory would be wrong, then everything could go down. Now the question is, would the theory be affected by clumping? Now to first order, you would expect that the line force is just basically the flux times the opacity gives you the line force. There's no particular reason why clumping should have a huge effect on that. But only the future will tell. So this is something we need to find out. Because there could be quite subtle effects in terms of, both the ionization could be affected, and there could be effects. So watch that. So, I've been talking about metallicity as if this is one parameter. But in reality, of course, metallicity involves all the different elements. CNO, silicon, sulfur, anything you can think of, iron as well. And it turns out it's actually quite important when you think about mass loss. Because here we have the case of solar metallicity, and here we have a case of 1/30th solar. If you look at my models, and I look at which elements actually dominate the driving, then for the solar case, 70%, 50 to 70% is due to just this one element of iron. And iron is not very abundant. But it has many, many millions of lines, and there are so many transitions that you can drive a lot of mass loss with just that element. With the CNO, which are much more abundant, they have only few lines. So their importance to the mass loss in the inner wind is not very high. And hydrogen and helium are not that relevant. But if you go to low metallicity, it turns out that these millions of iron lines, they don't have enough optical depth anymore to contribute significantly to the line force. And their contribution becomes very, very small. Whereas the CNO, their lines are strong, and they are still important at low metallicity. So the makeup of which elements dominate the wind at which metallicity, that changes. And why is this relevant? Well, there are many cases where this is relevant. People have been claiming very high mass loss rates for the first stars, driven by CNO, for instance. But if the CNO is not that important, then maybe the mass loss rate is not that important. So that's a relevant issue for O stars and rapidly rotating objects in the early universe. But we can have this effect already closer to home for Wolf-Rayet stars. Because if you look at a Wolf-Rayet star, it will start off with a little bit of CNO and a little bit of iron. And the iron will depend on in which galaxy it's sitting. What is the host metallicity of that galaxy? But at some point, these stars make elements. So if you have a 60 solar mass star on the main sequence, and due to mass loss, this mass goes down, of course. And here you see convective regions, overshooting, radiative zones, and so on. But you go from an O star phase, at some point you reach the Wolf-Rayet phase after a couple of million years. And if you look here, you reach a WC star, where the C means carbon is dominating the atmosphere. 40% of the mass is carbon. So the hydrogen that you have in an O star is now for a large part become carbon. So if this is a metal, and you have a metallicity-dependent wind, you have a huge mass loss rate. And for many years, people thought that Wolf-Rayet stars have such high mass loss rates because they have these metals, like carbon. But if iron is so dominant, because of the complex atomic structure, what is dominant here? Is carbon really important? Because there's so much of it? Or is iron important? So, I mean, I simplify the situation because in reality, silicon, phosphorus, all these elements will contribute to the driving. But if you want to simplify it, just as for understanding, if iron dominates the wind, then you expect Wolf-Rayet mass loss to be dependent on the host galaxy. A Wolf-Rayet star in the galaxy will have a higher mass loss rate than one in the SMC. Whereas what people do in stellar evolution, they say this is a metal, so you get metallicity-dependent winds. So they claim that it does not matter. If you have a Wolf-Rayet star, you have a high mass loss rate. And the whole memory of initial metallicity is wiped out. So this was the first time we did this in a differential study of metallicity-dependent calculation of mass loss of Wolf-Rayet stars, a pilot study, and you can see mass loss for the metallicity, the solar case again, 0, and you see that both WN stars and WC stars have a strong metallicity dependence. WN, the N is nitrogen rich. This is not because of advanced stages of nuclear burning. This is because of the CNO cycle. In a massive star, the hydrogen burning happens via the CNO cycle, so the nitrogen goes up and the carbon and oxygen go down. So that's the reason why the nitrogen is seen in the spectra. The carbon in WC stars, we really think this is helium burning products that have reached the surface. So you get carbon. Now the shapes are similar. The dependencies are a bit different. The WN star is steeper. That's not so surprising because it looks a bit more like an O star in terms of its chemical makeup. Whereas the WC star, the carbon starts to, because there's so much of it, it starts to dominate. But it's not completely flat. People previously thought it was just flat. It's not. It actually drops. But you also reach a plateau. At very low metallicities, maybe characteristics of the early universe metallicity, you actually reach a plateau. And that's because the carbon is still there, and it does contribute to the driving. So you will not end up with zero mass loss. Now the rates here, 10 to the minus 7, are quite low. But these are normal stars. These are just 10 solar mass Wolf-Rayet stars. If you start off with a 200 solar mass star, that's very close to the Eddington limit, all these rates will go up. So that story is still open. Now this WN and WC mass loss, it has consequences also for grammar errors, and I will go there. But you can test that also against observed ratios. In particular, the WC over WN ratio. Here are a couple of observations of nearby galaxies. The huge error bars, I should point out. But if you look at in the solar galactic area, you have a ratio of about 1. And if you have metallicity independent mass loss, like assumed in the MEDEA 2005 models, you would not expect a drop in this ratio because the mass loss does not really depend on metallicity. But if you have a mass loss rate, and here we have been varying the exponents somewhat to accommodate for the V-infinity dependence, which we can now do better. But all these cases, the strong dependence is the mass loss dependence, and you see that we get actually pretty good agreement, maybe surprisingly good, but that you can reproduce this drop in this ratio if you include metallicity dependent mass loss. So I think there is independent evidence for metallicity dependent mass loss in Wolf-Rayet stars if you look at the ratios in external galaxies. Now this all needs to be worked out much better because these are non-rotating models, single stars, and in reality I think this whole issue of Wolf-Rayet formation will also depend on rotation and on binarity. But as far as this ratio is concerned and its drop to low metallicity, I suspect that it's the metallicity dependence that is the main factor. So this is the same plot actually so this is the WC case, because that is the most interesting one in terms of gamma ray burst progenitors. In the old picture you would think no dependence, but in the new picture you would have a steep dependence. And if you drop your metallicity by 2 orders of magnitude, or even 1 order of magnitude, say, you drop the mass loss rate by a factor of 10, just almost. So it has a huge effect on stellar evolution. And so far, when I've been talking about mass loss, I've been talking about the peeling off of the surface, that you see deeper and deeper into the star. But if you take away mass from the star, you also take away angular momentum. These are rapidly rotating objects, and if you start removing mass, you can actually lose angular momentum. And that has been a problem for the Collapsar model for gamma ray bursts. Because basically, for this Collapsar model to work, this is the Collapsar model of Woosley, where you have a rapidly rotating stellar core, and you collapse to a black hole, and you form a jet, which, if it points towards us, will give rise to a long-duration gamma ray burst. But you need 2 ingredients for this to work. One is that the core is still rapidly rotating, and the other is that you have to get rid of your hydrogen envelope. If you have a red supergiant progenitor, then you have this huge hydrogen envelope, and if you have a jet, then the jet will not penetrate in short enough time for us to see a gamma ray burst. And that's the reason why people have been saying Wolf-Rayet stars are the likely progenitors of gamma ray burst. But, as I said earlier, massive stars have winds. So if you have a Wolf-Rayet star, and you have a strong wind, what happens to the angular momentum? It's all gone. So how do you still have a rapidly rotating object? There is a problem. But one way out is this metallicity-dependent mass loss. Because if you have less mass loss at low metallicity, you also lose less angular momentum, and you may still find a regime of parameter space where you can actually have rapidly rotating Wolf-Rayet stars at low metallicity. And in these 2 studies, where massive stars were modeled with very rapid rotation, you get strong mixing because of rotational mixing, and you have very low mass loss. So if you include my mass loss rates in these stellar evolution models, you can get it to work. And the prediction would be that you have long gamma ray burst favored at low metallicity. And there seems to be an observational evidence for that most long gamma ray bursts are indeed found in low metallicity systems. So this might well be, at least qualitatively, be a workable scenario. And it needs to be tested further, of course, because there are many uncertainties left for us to work on in terms of clumping in massive stars and in terms of rotational mixing in the stellar evolution models. But at least qualitatively, this may well be the key to the long GRB scenario at low metallicity. And just to remind you, if iron was not the driver of these winds, but if it was carbon, then this bias in the GRB phenomenon at low metallicity would not work. So that was the second issue I wanted to discuss. And the third one go back a bit closer to home, is the visibility jump. So what is it, and why is this interesting? So what is it? I'll show you a couple of spectra of B1 supergiants, and most B1 supergiants have strong p Cygni lines in carbon 4. So this is carbon 4, and this is carbon 2, and the terminal velocity is quite high here, you can measure. But then for this object, the carbon 4 is gone, and you suddenly have carbon 2 very strong, and the terminal velocity that you derive from this p Cygni profile is half of that you got there. So these are stars of the same spectral type, but they have completely different ionization structure and a completely different terminal velocity. And if you plot that in as a function of spectral type or temperature, so this is this terminal velocity over escape velocity versus temperature. Then for O stars, this is about 2.6. But at B1, you can have stars that have high terminal velocities, and you can have stars that have low terminal velocities. And at B supergiants, all have lower terminal velocities. This is referred to as the visibility jump. And there might be a second jump at spectral type A0. Now, this jump has been criticized by Crowder because basically at this point in time, when Lammers did this study, these stars were just put into the B1 bin, and they all had that temperature. But you can do a more sophisticated temperature analysis now with CMF-Gen, and it turns out that not all stars here have exactly the same temperature. So there's a bit of a temperature range, and that might even out this effect. So you get a more gradual change here. But what is absolutely clear is that the terminal velocities here are much lower than they are there. There's no controversy about that. The only controversy you could argue, if there is any controversy left, is whether you should call this a jump. And I'll come back to this. So interesting questions you may ask yourself. I mean, we know observationally these winds change character. The ionization is different. The wind velocity is different. What about the mass loss rate? Observationally, again, quite uncertain. But maybe what's the theory tell us? And then, of course, what causes this jump and what are the implications? So when I do Monte Carlo mass loss calculations, for O stars, I find relatively low mass loss rates. I mean, this is a low luminosity object. It's a 20 solar mass star. I call that a low mass star. And you get mass loss rates here, and you have terminal velocities of 2,000–3,000 kilometers per second. And when I calculate mass loss rates for B supergiants, I find mass loss rates are a factor 5 higher. Yeah? So the mass loss rate from theory is predicted to increase. So if you put everything together, you divide the O and the B supergiants. You say the O stars are driven by iron 4. The B supergiants are driven by iron 3. These have more lines, so have a higher mass loss rate, and therefore a slower wind. Whereas the hot O stars have a more moderate mass loss rate, but a faster wind. And in terms of the density of the circumstellar material, I mean, is the mass loss over the terminal velocity. So this factor 5 and 2 actually increases to a factor 10. So the density of the wind around B supergiant could be 10 times more than around an O star. And the reason why this could still be a jump is the following. When I do my calculations, I do it, time is stationary. So you don't get a runaway effect in my calculations. Or if you look at observations, you look at a sample of stars. But those stars will all have slightly different masses. But in reality, a real star may actually be, the following scenario might be most applicable, that there is a real jump. Because once the temperature drops, the iron recombines from iron 4 to 3, that's predicted, and then you get a line force increase, so the mass loss rate at the sonic point is higher than before, and you have a higher density. And the way the line-driven winds work is that the terminal velocity drops. But the point is that if the density is higher, that has exactly the same effect as the temperature dropping. So you get extra recombination. So you should actually, you have an extra loop here that you recombine even more. So the effect will be, it's a positive feedback effect, and you get a runaway. So in reality, a star might actually still really jump from one state to the next. And the question is this observed? Well, this is what you would expect. Should be relevant for massive star evolution, because when an O star evolves off the main sequence, it should encounter this jump. This is one position where it happens. And the other one is when the stars are a bit more evolved, have lost a lot of mass, and they're unstable as luminous blue variables. So luminous blue variables change their radius on timescales of years. Here they are in Hesper-Rotzer diagram. So this is the S Doradus instability strip, and this is where the stars are in minimum. Here they are in maximum, and on timescales of years they go back and forth. The Hesper-Rotzer diagram, just like that. And now the question is, what happens to this? This is the bistability jump. So we could actually test this bistability jump issue using LBVs. They should change their mass loss when stars do that. So AG Carina is the best studied LBV in terms of its sort of longer time spectral behavior. And Stahl et al. Have modeled the H-alpha line, and they found variations. Well, they didn't plot it, but I plotted it. So the mass loss rate versus temperatures. So the mass rates here for LBVs are higher. The reason is these stars have lost a lot of mass, so they're closer to the Eddington limit, so the mass rates are higher. And they're variable. So if you compare our models here and the data, well, a spectral analysis of H-alpha here, you see that the two show quite similar qualitative behavior. I mean, it's not a perfect agreement, but maybe we're onto something here. Even the amplitude of the changes are quite similar. It's a factor of a few. So this looks quite promising, that maybe individual stars, when they're in LBVs, they actually vary their mass loss on the kind of timescales we see in the observations. And I was really struck when I saw the following picture. These are radio supernovae light curves. The first time I saw this was this one, 2001 IG. It was a paper of Ryder et al. In 2004. I should maybe tell you a bit more how this is formed. So basically, the idea is that the radio emission comes from synchrotron emission because of the interaction of the supernova ejector with the circumstellar medium. So the source switches on, reaches a peak, and at some point there's a decline. And normally there's a parallel decline. For most supernovae, there's a parallel decline. But for this case, there's a sinusoidal modulation. It might be a bit difficult to see, but maybe you can see that there's a sinusoidal modulation. And Ryder et al. Interpreted this as due to a binary, so a Wolf-Rayet star with a binary companion, and the binary goes around it. And it disturbs the circumstellar medium of the primary, and you get a spiral structure. And Wolf-Rayet spiral structures, pinwheel nebulae, have been observed. So we know these systems exist, so it is a possibility. Although the scale of the system that Ryder et al. Require is actually off by a factor of 10. But the principle could work. But another scenario is you don't need a binary, you just have a variable wind, and you just have concentric shells. And then you may also find modulations like this. Now the question is, what kind of star could do that? You need to get the timescales right. For red supergiants, it's very difficult to do because the periods of red supergiant variability are quite long, and the wind's quite slow, and you don't get the right timescales. So we suggested, actually, first this paper came out, Soderberg et al. For 2003 BG, and they said, well, given that this object is so similar to this one, they thought that the binary hypothesis was a bit unlikely because you would need basically similar inclinations for both systems, and you need similar eccentricities for the binary. So it's an unlikely scenario. So they suggested it could be a Wolf-Rayet star. But I do not know of any variable Wolf-Rayet stars, so I thought it was quite unlikely. And we suggested that these behaviors could be due to LBVs. And, well, that would be quite controversial because, as I said earlier, LBVs are transitional objects where they have a lot of mass loss, and they should become Wolf-Rayet stars first, and then they should have hundreds of thousands of years of Wolf-Rayet evolution before you get a supernova. So it's highly controversial in terms of theory. But it seems, in terms of this type of observation, it seems to fit all criteria, whereas the others have more problems. The other scenarios have more problems. They can't be excluded, but they're less likely, maybe. So then it's basically the bistability jump in the supergiants of LBVs that produce these variations. Now, more recently, we noticed suddenly the following high-resolution spectrum of a type 2n supernova. Normally, when people look at supernovae, they take low-resolution spectra because the ejecta move very fast, tens of thousands of kilometers, so you don't need high resolution. But actually you do. So if you now have this supernova here, and you have a high-resolution spectrum, not only do you see absorptions of a few hundred kilometers, this is 200 kilometers, but you even have two components here. One is about 100 and one is about 200. And that looks a lot like a bistability jump, where the difference in the velocity is about a factor 2. If you compare that with observed H-alpha profiles of AG Carina, an LBV here, it's shown here, and here's another one, HD 160529, another galactic LBV. Also, there seems to be this kind of profile. So spectrally, they look very similar. So I think evidence is accumulating that LBVs explode. And that is contradictory to theory, because in the canonical picture, you have a hydrogen core burning object, then you become luminous blue variable, lose a lot of mass, make a stripped core Wolf-Rayet star, and after a few 100 million years, you get a 1BC supernova. If this is correct, then things are in a quite a different situation than we have always thought. So that is sort of where I want to leave you. So I'll just summarize what I've said before. So I showed you mass loss rates of O stars. I showed that we can predict the dependence with luminosity and metallicity. That doesn't mean everything is solved, because there's still this issue of clumping. But in terms of the relationship, the luminosity and metallicity, we do a pretty good job, I think. So as a function of temperature, we have this bistability jump between O and B. Still controversial whether it's a real jump, but there's definitely a temperature effect in terms of mass loss. And that may have consequences for the mass loss variability of luminous blue variables. And a bit more controversial, but it may even be that some LBVs could already explode. Thank you.
Okay, it's time for questions. Okay, I have one. In relation to the first stars, the first massive stars.
Yeah.
So you say that, if I understood you well, that the mass loss is going to be really small, no? Because they were very low metallicity, no?
There's a couple of issues. You are referring to this plot, yes, and the fact that for the Wolf-Rayet star here, the mass loss rates are 10 to the minus 7. So you would expect a dominant population, if there is a population of 40 solar mass stars or so, then I would not expect those to have a particularly high mass loss rate. But there could be stars that are more massive. And the point is, if a star is more massive, it's 60 or 80 solar masses, it is suddenly much more luminous. And the mass loss rate goes up quite a lot. And when you get close to the Eddington limit, you have very high mass loss rates. And you may not even need any metals, or only very few metals, to drive a very high mass loss rate. Yeah.
My question is how this change the evolution of this in relation to the next population of stars. So this have any consequence on the next stars or in the
if you have high mass loss?
So I mean, according to what you are finding, so how this change with our...
Well, we don't know that yet, because I cannot tell you. If you ask me, give me the mass loss rate of a zero metallicity star that is 120 solar masses. We need to do more mass loss calculations near the Eddington limit to understand mass loss there. Because the initial calculations I've done show that it's quite a dramatic effect. But that was also before we did the dynamics correctly, so that's another issue to take into account. It is you can't say if the mass loss rate is this, then the consequence is that, because you need to put the mass loss in a stellar model. Well, first of all, the mass loss will directly enrich the interstellar medium, so there's a direct effect, and then via its inclusion in the models, there will be indirect effect that you may get different products. So where in the old picture you might get at 150 solar masses you might get a pair-instability supernova. If you include mass loss, you may not get that. So it will change things in a non-linear way.
Any other question? Okay. So Jorick will be here around 4. So if anyone want to join him or for lunch, for example, or whatever, you have another opportunity for talking with him after the talk. Thank you very much for the talk.